Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to learn about the second cell in electrochemistry known as electrolytic cell. Recall this diagram. Electrolytic cell undergo opposite operations from voltaic cell, where it will start from electricity, then from this electricity, the chemical reactions will take place. Now we're going to look at the basic setup of an electrolytic cell. It's kind of similar to voltaic cell but with some amendments. It starts with only one beaker containing electrolyte. For this setup, we use potassium iodide solutions. And then we'll dissolve two pieces of electrodes in the solutions. These electrodes used is not necessarily the same as in its electrolytes. We'll talk about this later on. Next, we have wire to connect both electrodes. Note that we have something totally different in here from the one we have learned in voltaic cell, which are the battery and also the emitter. So what did they do? This cell involves non-spontaneous reactions, means the electron cannot move from one terminal to another by relying only on the electrode and also the electrolyte. Most commonly, inert electrodes are used in this cell, so they have no ability to attract ions of electrolytes on their own. Hence, a power supply, which is the battery, is needed to help to drive the reactions. And then we have this emitter connected to it. Function to tell how much current is supplied indicates there is electricity. Movement of electrons is always from anode to cathode, so we'll stick to anode on the left while cathode on the right. But the assignment of positive and negative terminal will differ from the voltaic cell due to non-spontaneous reactions. So we can determine the terminal by looking at the battery. Each battery got positive terminal with this longer line and negative terminal with this shorter line. Since the battery will play a major role in driving the reactions, so the side with shorter line will become the negative terminal, while the longer line here will become the positive terminal. In voltaic cell, we say negative means they got more electrons. That's why they can release electrons. But that phenomenon only applicable for spontaneous reactions, where the electrode has its own drive to start a reactions. In this electrolytic cell, electron will be discharged by attractions of the opposite charge. So the anode with positive terminal will attract this anion with negative charge. Then the anode will undergo the oxidation reactions, means the electrons will travel along the wire, approaching the cathode with negative terminal. And then this negative terminal will attract the cation of K+ with positive charge to balance the whole reaction, so we have reactions taking place at cathode. What matters now is which ions will be discharged at both cathode and anode for these non-spontaneous reactions. So, electrolyte plays a major role in here. Electrolyte can be either in molten or just water or aqueous state. Each and every time you are given electrolysis problem, you should first list all the possible cations and anions present in the electrolyte, and then sort them according to the electrodes they're going to be attracted. For the first case, we have this molten state. Molten state is a condition where solid is melted to become liquid under a very high temperature. If let's say you have molten NaCl in liquid states, it means the possible ions present are Cl- and also Na+. Cl- will be attracted to anode, while Na+ will be attracted to cathode. Even though water molecules contain both H+ and OH-, but they are hardly seen as separated ions due to strong hydrogen bond present. Therefore, they will be attracted as just water molecule. Often students make mistakes when forming half-cell equations involving water. Now, I'm going to explain to you very briefly how to construct one without just memorizing. At anode, water molecule alone will undergo oxidations, means water on the left releases electron and also oxygen gas on the right. On the left, we have both H and oxygen, while on the right, we have only oxygen. Hence, hydrogen plus should be added here. To balance the whole equations, we need to make sure that both sides got the same number of atoms. So we have 2 oxygen in here, but 1 oxygen in here. So times this H2O by 2. When we times it by 2, we have 4 hydrogen. Hence, we need to times H+ by 4. And the overall charge on the right hand side is positive 4, while 0 on the left means we're going to add 4 electrons to the right hand side. For cathode, water molecule will accept electron to form hydrogen gas on the right. On the left we have both H and O, while on the right we have only H. Hence, OH minus should be added here. We don't just add O2 minus because we are lacking of O. We add OH minus due to oxygens present in water is represented by OH minus. Then we need to make sure both sides got the same number of atoms. Look for the number of hydrogen on the right, we have 3 of them, but on the left we have 2. So by multiplying it with 2, we're going to have 4H, so we should add 2 OH minus on the right. And lastly, balance the total charge by adding 2 electrons on the left in here. So we can use both half-cell equations whenever we are dealing with water molecules. If you are dealing with an ACl in aqueous states, the 2 possible ions will be exactly the same as in molten states. They are Cl- to be attracted to anode and Na+ to be attracted to cathode. Apart from their state now has become aqueous instead of liquid, your electrolyte will have water molecules in it. Hence, you will need to consider water molecules as possible ions to be attracted to either anode or cathode as well. As shown in electrolysis of water just now, you will use exactly the same half-cell equations on respective electrodes. Having more than one possible ions present at each electrode means we need to decide on which species to be discharged. There will be few factors affecting the discharge of ions, but the main one, although other restrictions apply, gonna be standard reductions or electrode potential. In general, when there are 2 possible ions to be attracted at an electrode, you will need to choose a more positive value at the cathode and a more negative value at the anode. But since you will not be supplied with all these E-note values when answering electrolysis problem, then you will need to memorize this list. You must be familiar with this list back in high school. Note that there is an additional species of water for both cation and also anion. According to this list, the lower it is located, the easier it will be discharged. So let's apply knowledge we have learned to previous electrolytic cell. As for molten NaCl, even though you already know which ion to be discharged and you don't have to compare their E-note value, you will still need to form the redox equations indicates reactions is taking place. Rearrange the equations at anode should releases electron, while at cathode should accept electrons, and then make the number of electrons daily with one another. For this case, we have 2 electrons. Cancel them out and then you will get your overall equations. The question will further ask you about the product to be formed. You just need to look at the right hand side of each of the half-cell equations. Like at the anode, we have this chlorine gas as formed, while cathode we have this liquid sodium. You must emphasize their states as well, not just the name of species. Electrolysis of water will consist only water molecule at both anode and cathode. Just like we did in molten NaCl, we simply rearrange the half cell at anode to release electrons and cathode to accept electrons. Make the number of electrons tally with one another by multiplying the whole equations at cathode by 2. So we're going to have this 4H2O plus 4E to form 4OH minus and 2H2. Note that we have H2O on the same side, means we're going to add them. But then on the right hand side, we have 4OH minus and 4H plus that can make up the 4 water molecules. So 6 water molecules on the left and 4 water molecules on the right will give us 2 H2O water molecules left on the left hand side. So then we're going to take this O2 down here together with this 2H2 down here as part of our overall equations. As for product to be formed, we could conclude that anode will form oxygen gas, while cathode will form hydrogen gas. Next, aqueous sodium iodide will have more than one species to be discharged at an electrode. I changed the species a bit because NaCl will have an exception when it comes to second factor affecting species to be discharged. If you remember the E-note value, then you can simply compare their values. Anode will undergo oxidations, means it will favor a more negative E-note value. Hence, iodine will be selected. While for cathode, it will favor a more positive E-note value because they want to perform reduction reactions. Hence, we will choose water over sodium ion. If you didn't remember any of these values, take this list out of your mind and then choose the species that is located lower than the other one. You're gonna get the same species as before because iodine is located lower than that of the water in the list, and then the water in here is located below than the sodium. You don't need to show all this working when forming the overall equations. Marks will be rewarded starting from when you rearrange the equations at the anode and at the cathode, considering the correct species you have justified before. By having this number of electrons the same, then you are going to discard them and then lead to the overall equations of 2I minus plus 2H2O to form I2 plus 2OH minus and H2 gas. As for product to be formed, we could conclude that anode will form iodine solid, while cathode will form hydrogen gas. The question might also ask about the observations, but usually they will focus on what can be observed on the electrode. So we could say the purple-black solid deposited on the anode, while bubbling of gas at the cathode. The second factor to affect the species to be discharged is going to be concentrations. Note that this factor only be considered when you have aqueous states. They will only affect the discharge of anions. So the exceptions that you need to properly address here are an ion with high concentrations is likely to be oxidized. That's when the solutions be termed as diluted and concentrated. But this term only applies when you have chlorine in your solutions. This is because chlorine here is located above water. If you stick to only E naught value we have discussed in the first factor, both diluted and concentrated solutions will discharge only water, which already neglect the concentrations factor. Other than solutions containing Cl, like Br or I, they don't have to use such diluted or concentrated terms because their E naught value is already below than that of the water. So in any concentrations, they will still be discharged. Other than anions with high concentrations, oxo-anion means an ion that has oxygen such as SO42- and O3-. They will not oxidize as their oxidation state is already high. So water will automatically be discharged. Aqueous sodium chloride will be divided into two concentrations. One is diluted, another one is concentrated. Again, you need to compare their E naught value by using either SRP table or the ion discharge list. Diluted means you have more water in it, so by right you tend to discharge them, but still you need to check on their ability to be discharged. Both E naught value and also the list will suggest water to be discharged. This is because on the anode they got more negative value, on the cathode they got more positive value. Same goes to the list. H2O is located below than that of Na and also Cl. Hence, half equations at the anode and cathode will be on water. So basically, they are the same as in electrolysis of water, where we need to make this number of electrons equal to 4. These 4H plus and 4OH minus can combine to form water. Then we also got water on here, so 6 minus 4 will get 2H2O liquid on the left, and then oxygen gas and hydrogen gas on the right. Product to be formed at the anode will be oxygen gas, while at the cathode will be hydrogen gas. How do we know this? By looking at the half cell equations. On the right hand side we have O2 and also H2. As for observations, since our product involved only gas, you could write bubbling of gas formed for both anode and cathode. If you have concentrated NaCl, we know this applies to only anions. By right, you got a significant amount of Cl minus than the water. Even though its E naught value doesn't suggest it to be discharged, we'll still choose Cl minus over water for anode. As for cathode, simply look at the E naught value. We'll say this water to be discharged. So we're going to put it on anode for oxidations and cathode for reductions, and then balance the equations by discarding these two electrons. And lastly, we'll get overall equations of 2Cl minus plus 2H2O to form Cl2 gas, 2OH minus and also H2 gas. Lastly, product to be formed at the anode will be chlorine gas, at the cathode will be hydrogen gas. As for observations, it will only be bubbling of gas formed. Aqueous sodium sulphate is an example where you have oxo-anion. And these also anion will not be oxidized due to high oxidation states. You could see from the list they are located higher up here. So they will automatically be disqualified. Hence at anode, water will be discharged. While for cathode, check for a more positive value, and this time we got Ag as a more positive value, hence Ag will be discharged. If we look at the list as well, we have Ag lower than that of the water. Rearrange the equations at both anode and cathode to be oxidations and reductions, and then balance both equations by making the number of electrons equal, and then cancel them. Your overall equations will have 4Ag plus 2H2O to form O2 plus 4H plus and 4Ag solid. Product to be formed at the anode will be oxygen gas, while at the cathode will be the silver solid. As for observations, it will be bubbling of gas at the anode, while gray solid deposited, or you could say mass of electron increase for the cathode. The last factor that will affect the discharge of species is the nature of electrodes. They will somehow affect the ions selected to be discharged at the electrodes. In most electrolysis, we'll use inert electrodes because they are not going to involve in the reactions. But there are also cases where we use active electrodes. This active electrode means they are able to take part in the reactions, as in to be listed as species to be discharged apart from species present in the electrolyte. Example of active electrodes that may take part in the reactions could be any metal ion listed here. Let's say we're going to conduct electrolysis of lead to nitrate solutions by using PB electrodes. You can also use active electrodes for only one electrode at a time, but I'm going to show you if you have both active electrodes. First thing to do is to sort all possible cations and anions accordingly. In these electrolytes, we have NO3-, H2O, and also Pb2+. These NO3- and water will be attracted to anode, while this Pb2+ and water will be attracted to cathode. Now we are left with our active electrode of Pb. Since anode hasn't got any Pb in its possible ions, so we have to add them up. Meanwhile, cathode already got Pb2+ as its possible ions, then we can assume we already include them as our selections. Now let's check their compatibility to be discharged. Pb2+ is located below than that of water with negative 0.13 volt, which is more negative than the positive 1.23 volt of water. Hence, Pb will be discharged at the anode. While for cathode, check for a more positive value. This time, Pb2+ got a more positive value than the water. Therefore, Pb will be discharged. Since we already have these two electrons on both anode and cathode, we can cancel them out to give overall equations consisting only Pb solid and also Pb aqueous. Product to be formed at the anode is no longer gas, but we could write it as Pb ion 2+ is released, while for the cathode we got lead solid. As for observations, since ion of electrode has been discharged, we should expect the mass of electrode to decrease, while for cathode, mass of electrode will increase because some of the Pb solid will be deposited on the cathode. We're going to use Faraday's law of electrolysis for any calculations involved in an electrolytic cell, as this law describes the relationship between the amount of electricity passed through the cell and the amount of substance produced at the electrode. Faraday's law that we can add is the Faraday's first law. It states the amount of substance with this symbol M produced at each electrode is directly proportional to the quantity of charge flowing through the cell, which with this symbol Q. Every mole of electrons will be referred as 1 Faraday's, that is equal to 96,500 Coulomb. We will use this constant to find electrical charge in Coulomb exhibited theoretically by a reactions based on the number of electrons present in the half equations. To find how much electrical charge exhibited by the reactions in experiment, we will use formula of Q is equal to IT, where Q is our charge with unit of Coulomb, current is I with unit of ampere, and time with the unit of second. Let's try to solve this problem regarding Faraday's first law of electrolysis. A current of 2.00 amp is passed for 30 minutes through an electrolytic cell consisting of graphite electrode and a solution of potassium sulphate at 25 degrees C. Calculate the volume of oxygen gas evolved at the anode at 180 amp. So you're given current of 2 amp and also time of 30 minutes. So you can simply find the electrical charge for the whole reactions. We can use the formula of Q is equal to IT. You can keep the I as 2 amp, but the time here in 30 minutes, you should change it to second. So 2 times 30 minutes times with 60 seconds will give you the Q of 3600 coulomb. So this charge belongs to only the reactions that happened when this current is applied for this amount of time. But then we want to find the volume of oxygen gas evolved at the anode, means at our anode, we aim to get the product of oxygen gas. So let's try to relate it to the half-cell equations. From these half-cell equations, we get to know the electrical charge theoretically by relating it to the amount of electrons present in here. So we could say for every 1 mole of O2 will require 4 electrons. So for each electron equal to 1 Faraday. Each Faraday equals to 96,500 coulomb. So we could say when we have 1 mole of O2, 386,000 coulomb. Means if we have this 3600 coulombs, they will require 9.3264 10 to the power of -3 mole of O2. So from this number of mole, we get to know the volume of oxygen gas evolved at room temperature as stated here, 25 degrees C. So we know volume at room temperature equal to 24 liters. So if we have this amount of mole, we need to times it by 24, and lastly we'll get 0.224 liter of oxygen gas evolved at the anode at RTP. That's all for electrolytic cell, and that marks the end of this chapter 3. Goodbye.